Welcome back. This is the third segment of section 2.1. I've been trying to keep these videos a little bit shorter and a little more compact, so this is the third segment, even though we've only had about half an hour's worth of material. So as promised from last time, I want to start applying some of these ideas with some sample problems that we'll work through here in just a second, and I'm going to try to keep them relatively simple. Because they obviously get harder as we go through the course. A little bit off center here. Okay, so this is, again, this is section 2.1, and I believe we are now on page 4. So let's consider a triangle. Let's consider a right triangle. And we will give it labels A, B, and C. This is the right angle here. We will take, we will say this side is equal to, this is little a is equal to 36, little b is equal to 77, and little c is equal to 85. Now, it turns out that the Pythagorean theorem is sort of, the converse is true too. So if a triangle is right, then the sum of the square of the legs is equal to the square of the hypotenuse. In mathematical logic, if A is true, then B is true, does not necessarily mean that if B is true, then A is true. That's what's called the converse in logic, where you know, and the classic example is to say, to use grades, for example. So if your instructor would say, if you get an A on this test, then your grade will be a B in the course. That could be true. And if it is true, then it certainly does not imply the converse, which is that if you get a B in this course, then you got an A on the test, right? It's a subtle difference. But it turns out with the Pythagorean theorem that it's actually the converse is true as well. So if the sum of the squares of the lengths of the legs of a triangle are equal to the square of the third side, so any two sides, if the square of their distances summed is equal to the square of the third side, then that triangle is a right triangle. And then you can start talking about legs and hypotenuse. So we can just quickly verify that this is in fact a right triangle. So 36, to test it, 36 squared plus 77 squared, does this in fact equal the square of 85? And I'm just going to pull out my calculator here. It's a little hard to see sometimes because of the lighting and everything else, but I'll just verify. So 36 squared plus 77 squared is equal to 7225. And then I'm going to go ahead and take the square root of that and notice that it's actually equal to 85. So from this, we know for in fact that this is a right triangle. Now, what we'd like to do with this is we would like to find, let's do find all trig functions, so all 6 of them, of angle A and B. Okay, so let's run through them fairly quickly. Now, sine of A, using our mnemonic, is opposite over adjacent. So opposite over hypotenuse. So opposite is 36, hypotenuse is 85. This will be 36 over 85. Don't use a calculator, right? We're in fact, I'm trying to encourage you to never use a calculator unless it's something that's derived from measurement. What about the cosine of A? Well, notice that the cosine is the adjacent over hypotenuse. So this is 77 over 85. The tangent of A is the opposite over adjacent. So that's 36, equals 36 over 77. And then, of course, the reciprocal functions So cosecant of A is equal to, just flip this upside down, we have 85 over 36. The secant, flip this one upside down, is 85 over 77. And then, of course, the cotangent of A, flip this one upside down, is 77 over 36. Okay, so what about angle B? Well, sine of B, now we're looking at it from this angle, is the opposite over the hypotenuse, so 77 over 85. And I'm just going to draw attention to the fact that these two numbers are the same, right? Because A and B are complements of each other, and so their co-functions should have the same value. And so without too much extra, we can say that cosine of B is 36 over 85, and tangent of B is 77 over 36. So cosecant of B, now we use the reciprocal, secant of B reciprocal, and cotangent of B reciprocal. And notice I didn't even refer back to the triangle to get these. I'm just looking at how what the relationship is between. I'm kind of making this note so you see it's different angles, but just the relationship between all these functions. Because yes, there is a representation, this triangle, for which these things are true, but it turns out that these obey all of those other identities. These particular fractions, tangent of this particular angle, which has this value, happens to be the ratio of sine to cosine, etc. So, all right, so the mnemonic allows us to take a right triangle and produce trig functions of those angles, the acute angles. But here's something that I notice people always seem to get a little bit confused on, because they want to use this sort of cheat for everything. So let me just ask you real quickly, what is the sine of angle C? Looking back at the triangle, the first thing that I see students do when you ask them this question is they start to go, well, which one's the opposite, right? Because it looks like the hypotenuse is the opposite. I hope everybody sees why that might be a problem. But just remember, the mnemonic is not a substitution for what we know about trig functions. Angle C is 90 degrees. So you already know what the sine of 90 degrees is. And the mnemonic doesn't help you. You just simply need to know that that's 1, right? And similarly, I don't need to do them all because we have done them all. But just as an example, how about cotangent of C? Now, if you look back at the triangle, you're going to say, well, cotangent is adjacent over opposite. And you're looking at maybe some combination of these or whatever else. But again, that does not hold water because the triangle doesn't represent the reality. Remember, the cotangent of 90 degrees is in fact 0. Okay, so don't, like I said, don't confuse the mnemonic for something that it's not. All right, so real quickly, I want to sort of write out some examples. Let's see, section 2.1. Now we're on page 5, I believe. Yeah. Okay. So let's do some quick examples of some things that you might see in the homework. So write each in terms of its cofunction. I think these sort of problems are really just designed to try to get you familiar with the term cofunction. So let's just do a couple of them. So sine of 9 degrees. Okay, so sine of 9 degrees, what this question is asking you is to write that in terms of cosine of some angle, which is going to be cosine of 90 degrees minus 9 degrees, which is cosine of 81 degrees. So this is sort of the result that they're looking for. A sine of 9 degrees is equal to cosine of 81. Let's do a couple more here. How about one involving cotangent? So cotangent of 76 degrees, well, that's equal, the cofunction of cotangent is tangent. So we're talking about tangent of 90 degrees minus 76 degrees, which happens to be equal to the tangent of 14 degrees. Let's do one more involving secant and cosecant. So cosecant of, let's say 43 degrees is equal to the secant of 90 degrees minus 43 degrees, which is the secant of 47 degrees. Okay, so it's sort of some quick and easy problems that, like I said, I think there's a couple in the text, and for whatever reason, when students see that, they're not really sure what to do. Now, we can abstract this a little bit and try to solve for a variable inside these arguments, which is kind of a new sort of thing. So you'll see some problems that look a little bit like this. So suppose cotangent of theta minus 8 degrees is equal to tangent of 4 theta plus 13 degrees. Oops, kind of ran out of space there. Okay, so we had problems like this in chapter 1, where it's like, well, you know, so I can use a reciprocal identity to connect these up, but that's not going to get you anywhere with this particular one. You have to almost recognize that there's a relationship between tangent and cotangent that we can exploit that allows you to write this directly without having a reciprocal or something like that in place. So note, and you can start with either one or the other, it doesn't really matter, but note that cotangent of theta minus 8 degrees is equal to, just like we did up here, 90 minus whatever's in here. So you got to be careful with parentheses and whatnot, but this is tangent of 90 degrees minus theta minus 8 degrees, right? Which happens to work out to tangent of 98 degrees minus theta. Okay, so we've sort of transformed the left-hand side to something involving tangent, and you recall that we said a solution to this is where this argument is equal to this argument. So now we have 98 degrees minus theta equal to 4 theta plus 13. So if we kind of break that down, we have 5 theta equal to 85 degrees. And so if I remember correctly, I think theta is equal to 17 degrees. So there's our A solution to this equation. We could try it with another one. Let's go ahead and do another one just to nail that home. So now I think we're on page 6. Okay, so again, suppose that the secant of 5 theta plus 14 degrees is equal to the cosecant of 2 theta minus 8 degrees. Okay, so as before, what we want to make sure of is that we recognize that we're comparing two cofunctions. That's sort of the key to these sorts of solutions, is that there isn't, I mean, there is no reciprocal relationship between these. There's a Pythagorean sort of somewhat of a, I mean, we can mash something in there. We can make a direct relationship between secant and cosecant. We already have one, which is the cofunction identity. So pick one of them. It doesn't really matter which one. Let's go with cosecant. So recall that cosecant of 2 theta minus 8 degrees is equal to the secant of 90 degrees minus whatever's inside here. So that's 2 theta minus 8 degrees. And again, be careful with SIGNs in parentheses. This is actually going to make this secant of 98 degrees minus 2 theta. Okay, so now I can compare the left-hand side to the right-hand side, and because of the same function, one solution is just to simply say that this argument is equal to this argument. So 5 theta plus 14 degrees equal to 98 degrees minus 2 theta is a solution. And so when we solve this, we end up with 7 theta equal to 84 degrees, which implies that theta is equal to, is that 12? Yeah, 12 degrees. Okay. So I'm just going to say a couple things here. Again, there are many, many solutions to this. So we've found a solution to both of these. In fact, there's an infinite number of answers, and there's for any one particular one of these, there's actually, quite a few just between 0 and 360 degrees. I think for this particular equation, there could be as many as 10. But if you tried some graphing techniques, maybe you could get that down just a little bit more. One other thing, and since I've kind of got it here, and this seems like a good place to talk about it, I want to make a statement about the trig functions in quadrant 1. So so let's say it this way: given theta in quadrant 1, okay, as theta increases, so this is kind of like we're talking about some functional analysis here. So imagine you start with an angle basically at 0, and as it cranks up, goes from 0 to 90 degrees, we can make some statements about these functions. Sine of theta is increasing, and that's a term from college algebra, right? It means that the output continues to go up. It doesn't like jiggle around, be bigger, larger. It doesn't have any sort of things like that. Cosine, because it is the cofunction, actually decreases. Tangent is increasing. And so its reciprocal function, cotangent, is decreasing. Secant is increasing. And cosecant is decreasing. So we're talking about some interrelationships here. You're like, well, why is this one called, why do some of them have the co in front of them and some of them don't? Well, this is the reason why, is because one of the reasons why, but the increasing functions are given the regular name, sine, tangent, secant, and the decreasing cofunctions are given the co in front of them. So cosine, cotangent, cosecant. Okay, so I think I'm gonna leave it at that for the time being. The next segment, we're gonna come back and we're gonna actually work on trying to find these exact values using some geometric proofs. We're gonna try to find the exact values of sine, cosine, tangent of very specific angles. Those angles will be 30 degrees, 45 degrees, 60 degrees. And then I may do this, I may do it for 18 as well, but only for a very kind of small section. I will only probably do it for sine. It's worth doing because it kind of brings back some of that algebraic skill involving rational functions and rational equations. So we'll see. Depends on how much time I end up spending on this. I may just put it as like a supplement. But I will see you again very, very